That thing yells at you, but it's turned off right now. So the numbers above the elements are how many elements are attached. I don't know what that means.
So like if you look at the periodic table, there's like a number above it.
This table? Oh, sorry.
The periodic table.
This one?
E.
So there's several numbers. Let's just do the easiest one. Hydrogen, the first one. So the H is the symbol. The one above the H is the number of protons in the element. The number of protons is the element. If you change the number of protons, you don't have that element anymore. So that's what my master's degree was about, which was nuclear chemistry, where we were changing the number of protons in elements to see what would happen. So every element after number 92, which is uranium, are humans screwing around with nuclei by adding protons to them. So if number 92 is it, nature does not put more than 92 protons in a nucleus by itself. So from 93 all the way up to 118, that's us throwing atoms of specific sizes at other atoms of specific sizes and hoping that they smash together and hold on. And for the most part, they're useless. There are only two of the elements that have any use, and it's number 94, which is plutonium, which, I mean, I'm sure you know what plutonium does, and number 95, which is americium. That gets used in smoke detectors, some smoke detectors. So don't crack open your smoke detector, scrape off the detection portion of it, and eat it. That would be bad. But outside of doing that, your smoke detector cannot hurt you. So the number below the H is the average atomic mass of hydrogen. It's actually a weighted average atomic mass. So let's talk about what a weighted average is for a sec. So let's say that you took 4 classes this quarter, you got 2 A's and you got 2 C's. So what's your average? 3.
B.
3.0. It's a B average, right? A's are worth 4, C's are worth 2, and B's worth 3. So you'd end up with an average of 3, a 3.0. But what if you got 3 A's and 1 C? Do you still have a 3.0?
3.5.
It's not a 3.5, but it's like a 3.25 maybe. But it's higher than a 3, right? And it's because you had 3 A's. So you're weighted higher than, you don't just take the average. I don't just take a 4 and a 2, divide by, and then get an average of that. So since you had 3 of the 4s, then that adds up to 12. And then you had 2 from the C, add those together and divide by 16, which was your total possible. And so whatever 14 divided by 16 is, 7 divided by 8, I don't know, like 3.25, somewhere in that area. So what that's saying is this mass number that's underneath the hydrogen, it's saying that almost all the hydrogens in the universe have a mass of 1, but they don't all have a mass of 1. So this discussion that we're having right now is about something called isotopes. So let me share. I'm going to kill that. Hey, die. Why is this taking so long? Share this. Okay, so all of a sudden my computer just got super slow. This is a symbol. Doesn't look like you can see that. I don't understand. What are you guys seeing right now?
H1.
You do see that?
Yeah.
Okay. All right. So this is the nomenclature that chemists and physicists use to talk about isotopes. So what this is saying is this is a hydrogen, and this hydrogen has a mass of 1. And every hydrogen in the universe has one proton in it. And since all elements or all substances in the universe have protons and neutrons and electrons in them, a proton has a mass of 1, and this is used in the unit they use is atomic mass units. The neutrons have a mass of 1, and effectively the electrons have a mass of 0. So if I'm an atom and I lose an electron, it's such a small amount of mass that we don't even bother calculating out how much mass it lost. So sort of like you lose 1 hair. It's not like anybody's going to say, oh, hey, looks like you lost weight. Nothing like that's going to happen. So this number right here, this 1, is this particular isotope's total AMU. And so this H here is referring to hydrogen, and all hydrogens must have 1 proton. Have to have 1 proton or they're not hydrogen. In the same way that all carbon atoms must have 6 protons or they're not carbon atoms. So what is in this particular hydrogen isotope? The only thing that's in this is 1 proton and 1 electron. The electron, again, the electron's mass doesn't really matter, so I don't really care about that. And I know since all hydrogens have to have at least 1 proton, then this 1 right here is from the proton. All right, so let me do some erasing. All right, so tell me about this isotope. You guys can still hear me, right?
Proton, 1 neutron?
Right. So the reason you knew, the reason I know that this is 1 proton and 1 neutron is this has an H. So that automatically says I've got 1 proton. But this thing has a total mass equal to 2. And I know one of them is that proton. So that means the other one must be a neutron. So this is hydrogen 2. It actually has a name. It's called deuterium. All right. And so then there's one more option. The other option is, let me use a different color. The other option is H3. So tell me about H3.
Ton and
it's a hydrogen, so it has to have 1 proton, and it can only have 1 proton. So that takes care
2
of,
neutron.
and so that leaves me with a mass of 2, which must be 2 neutrons. And this is tritium, the isotope of tritium. So this is all we know about hydrogen. Hydrogen can have 1 proton, or it can have 1 proton and 1 neutron, or it can have 1 proton and 2 neutrons. Those are all the known isotopes. So great. If I were to take the average of hydrogen 1, hydrogen 2, and hydrogen 3, what should that number be? Should be 2, right? 1, 3, 6 divided by 3 gives me a mass of 2. So the average mass of all the known isotopes is 2. But this is a weighted average. So what is this saying about the hydrogens in the universe? The fact that the number is 1.008. What this is saying is most of the hydrogens in the universe are hydrogen 1. Just like if you added up all of the grades you ever got, like from, say, your freshman year of high school through now, if you got 99.9% A's and you got 1 B and so you got 2 B's somewhere along the line and you got 1 C, your GPA is not a 3.0. It's like a 3.9998 or something like that. Does that make sense? I can't see you guys, so you're gonna have to say something.
Yes, that makes sense.
Okay, so let's take this and look at the periodic table for a sec. So I want you to tell me about carbon. In your typical carbon atom, how many protons and neutrons are on a typical carbon atom? So carbon is element number 6. So what do you know about carbon? It's got 6 protons in it. You know that for a fact. Okay? Why? Because it's element number 6. To answer your question about memorizing the periodic table, no. I mean, you guys are at home taking these exams, so you're going to have access to the periodic table. If you were in my class live, you would have a periodic table with you. There's zero reason to memorize the things on the table. Okay, so look at the mass number underneath the C on element number 6, carbon. It's 12.01. So what does that say is the mass of most carbons? $12. So most carbons have a mass of 12. So if all carbons have 6 protons in them, and this carbon that we're talking about has a mass of 12, how many neutrons does it have in it? 6. Because the neutrons have a mass of 1 and the protons have a mass of 1. If I know there are 6 protons, then all the rest of the mass has to be neutrons. And so that leaves me with 6. So there are other isotopes of carbon out there. You've probably heard of carbon-14. They talk about carbon-14 with carbon dating, and they can tell how old like a bowl is, or like a wooden bowl that somebody made and they found in like an archaeological dig in, I don't know, Colombia. So, okay, this spoon is 7,000 years old. So that's because the version of carbon that has a mass of 14 is radioactive. So you've got some of that inside of you, and trees have some of that inside of you, and anything that's got a carbon in it has some of that inside of them. So once the tree or you or whatever is made out of carbon dies, then the only way to get rid of the carbon is through radioactive decay. And so if you know how much it had, then you know how much it's got, then you know how long it's been sitting there. So if I told you that there was carbon-14, so what are the things in the nucleus? It's carbon-14. So what do you know has to be there? It's carbon. So what has to be there? It's element number 6. So 6 protons have to be there. Okay? So if it's carbon-14, then 6 minus 14 leaves us with 8. And that 8 mass, what is that? Those are just neutrons. So it's got a mass of 14 because it's got 6 protons. It has to because it's carbon. And then all the rest of that mass is neutrons. So then there's 8 neutrons left. So
I really wish you could draw pictures.
You wish I could draw pictures? Okay. No, I can draw pictures. I can go back over here.
Okay.
All right, so let's do, how about sulfur? So on your table it says 16S 32 point, what is it? 07. So there's the atomic number, the number of protons, there's its symbol, and there's its weighted mass. So if we were talking about sulfur and I put sulfur S-32, which most sulfurs have a mass of about 32. So tell me about this sulfur. How many protons are there? How do I know that it's 16? It's element number 16. When you look at sulfur on the periodic table, there's a 16 above the S. So all sulfurs have to have a 16. So what's left over? right? 32 minus 16. And this all has to be equal to the number of neutrons.
0.7.
No, not 0.7. I'm not talking about this one. I'm talking about this over here. All right? So you can't have this. This thing here doesn't exist. Just
I don't
like,
see any pictures on the screen. I just see you.
Me neither.
oh, damn it.
I was like, what are you talking about?
It says I'm viewing your screen, but I'm not.
How about that?
Here we go. There we go.
That better?
Okay.
Okay, so a sulfur atom that has a number of 32 for its mass. So 16 of that must be protons because it's sulfur, and then all the rest of this 32 must be neutrons. So this particular isotope of sulfur called sulfur 32 has 16 protons and 16 neutrons. Tell me about sulfur 33.
Half.
Sorry, say that again?
16.5.
No,
Can you have half a proton and a neutron?
cannot have half of any of those things.
Okay.
It still has 16 protons. How are you supposed to know that? Because on the table it says 16. It has this is just
okay.
drawn on the table, right? So then this 16 number is fixed. It's
Yeah.
saying that there are 16 protons always. So now if I take 16 away from this, I'm left with 17. And what's that 17 number?
A neutron.
It's the number of neutrons. So sulfurs with a mass of 32 exist. How do you know that? Because the number underneath sulfur on the periodic table, 32.07, isn't exactly 32, which means some sulfurs are bigger than 32. So it's not an average, it's a weighted average. So if you were to just reach in and grab a sulfur out of a bag of sulfurs, what would be the mass of the sulfur you grabbed? Probably be 32, but it could be 33. There would be a low chance that you'd grab number 33, one with a mass of 33, but it's possible. You okay with that?
Why is that?
It's the way it is.
Okay.
That the nucleus can have will have a set number of protons for that element, but the number of neutrons can vary, and sometimes the variation makes the nucleus unstable, which means it's radioactive, and sometimes it doesn't care. So we had that discussion about carbon-14 being radioactive and carbon-12 not. Well, carbon-13 is also not radioactive. So sometimes it makes it radioactive and sometimes it doesn't. So
With an unstable nucleus, does that make it radioactive?
yes, so something that's radioactive, the definition of a radioactive element is an element that has an unstable nucleus. And you get an unstable nucleus by having the wrong ratio of protons to neutrons. And that's as definitive as I can get. Sometimes the right ratio is equal numbers, and sometimes the right ratio is 10 extra neutrons. It just depends on the element itself. What do you think the neutrons are for? The protons are positively charged, and the electrons are negatively charged, and the neutrons have no charge at all.
Like neutral?
Yeah, so why would you have a neutral substance?
Balance the rest out.
No, because the electrons balance out the plus charges. So in, say, like a helium atom, there are 2 protons and 2 electrons. So that's 2 pluses and 2 minuses, and that cancels everything out. So it took scientists about 33 years to figure out that there was another thing there. Because we found the pluses and we found the minuses, why the heck would there be a nothing charge? So what do you know about things that have the same charge? Do they like each other or not like each other? What happens when you try to put the north pole of 2 different magnets next to each other? They push away really hard. So that's the same thing with positive charges. The term opposites attract is talking about protons and electrons. So protons and electrons are attracted to each other because one's positive and one's negative. So the protons themselves are stuck in the nucleus, which is this ridiculously tightly packed space. I mean, the size of the nucleus itself is like 10 to the negative 15th meters. So a ridiculously tiny size. And inside of that, I've got all my protons stuck inside of there. So if I was a nucleus and there were, if I was a sulfur nucleus and I had 16 protons all stuck to each other really closely, they wouldn't want to be right on top of each other. So what does nature do? It basically just shoves neutrons in between them. Does that make sense? So if you had a 4-year-old here and a 4-year-old here, and they were fighting each other, what could you do? You could put a wall in between them, right? You're in this bedroom and you're in this bedroom. Now you're not, now you're okay with being next to each other, right? So the neutron is sort of like the wall of the nucleus. It keeps the positive charged things that don't want to be touching each other just far enough apart so the nucleus doesn't fly apart. So what if the nucleus doesn't have enough of those neutrons in it?
Becomes unbalanced.
Then it's radioactive. Then it's unstable and it tries to shoot particles out of it till it gets to become stable again. So all of the elements after bismuth, number 83, it doesn't matter what their ratio is, they're all radioactive. So bismuth is a few down from gold. And so 83, 84, 85, 86, all the way up to 118, all of those elements are radioactive at all times. There's no way to make them not radioactive. That's not saying that elements less than 83 are not radioactive. It's just there are versions of them that are not radioactive. Except for number 43, technetium, and number 61, promethium. Those two, they're just radioactive, period. It seems for some reason that we don't understand yet that any atom that's got 43 protons in it is unstable, and any atom that's got 61 protons in it is unstable. And these are things we would like to understand, but we don't yet. Okay, so does that help with explaining what the little boxes on the table mean?
Yes.
We had a discussion last time about why the periodic table looks weird. Do you remember that? So the reason that there's like that huge blank section where it like divots down and then comes back up is because the person who came up with the table stacked things that have similar chemical reactivity in the same columns. So the discussion that we had last class was, what do we use fluorine for? We use it to decontaminate water. So people will fluorinate water in big cities and whatnot because they don't want to get cholera or, I don't know, they don't want to get the cryptosporidium bacteria. So fluorine kills bacteria. Well, what do you know chlorine does? Kills stuff, right? That's why they put it in swimming pools. What do you think, since bromine is in the same column as chlorine and fluorine, what do you think bromine does? Kills stuff. Iodine's in the same column, so what do you think it does? Kills stuff. So he stacked these things in the same column because they chemically react similarly to each other. And that's it. So the reason that there isn't anything, the reason that the second element, helium, is not right next to the hydrogen, that it's all the way on the far side of the table, is because helium behaves like everybody else in that column there, the neon, argon, krypton column. And it doesn't behave anything like the beryllium, magnesium, calcium, strontium column. So the table looks weird, but it's actually not. Gold is element number 79. It's sort of in the middle-ish in the table. Do we see it? Look at the element right above it. Do we know what that is? Ag is silver. What do you know about the element right above that? That's copper. So why do you think copper, silver, and gold are all in the same column? They're all chemically similar to each other, right? What have we traditionally used copper, silver, and gold for?
Monetary.
Money.
Coin.
Coin. So why am I making money out of copper, silver, and gold? Why don't I use zinc? Because zinc is way, way cheaper. Why not use zinc instead of copper? Because zinc is very, very chemically reactive. If I gave you like a coin and it was made out of zinc, just touching your hands would cause it to rust. The thing would basically disappear just sitting on a counter after, I don't know, not disappear, but it would convert from a metal into a salt or an oxide in like a week. If you dropped it into water before the end of the day, there really wouldn't be anything left of it. So the reason we chose copper, silver, and gold to be money is because if I take my gold coin and I give it to you, you know that gold coin is going to sit there and be a gold coin later on when you want to spend it. Same thing with jewelry, right? You don't want to give somebody like a beautiful wedding ring made out of zinc and 3 days later it's like cut and then falls off of them. Okay. Do you want to talk about something else with the table? Or are you good with that so far?
32.07 on my table.
It doesn't say that?
Well, not on the book one.
32.07?
Yeah, it just has like the numbers.
What page is that on?
If you go to the pictures on the Moodle, that's where I printed out mine,
Oh, really?
and it has
What-
everything on it.
Callie, what page are you on?
32.
Okay. Yeah, the one I'm talking about is go to the back inside cover.
Oh, nice.
So this one here was just talking about the number of protons in the atoms. So it hadn't gotten to isotopes yet. So that's why 32 doesn't have those numbers. We should probably talk a little bit about naming stuff. So, sorry. So, what's the name of this molecule?
And dioxide?
Carbon dioxide. Why is this guy named carbon dioxide?
1 carbon, 2 oxygen.
Yeah, so in the book, page...
Di is 2.
Yeah, di is 2, so it's page 36.
36.
On the top of page 36, it shows you a table. And that table is telling you what prefixes are for covalent molecules. So this is a covalent molecule, and the reason I know it's a covalent molecule is it's atoms that are nonmetals. So how do I know it's nonmetals? So can you guys still see me?
Tiny. You're small.
So on the periodic table on page 32, if you look at it, there's some elements that are in green and some that are in like pinkish color and some that are in blue. So the elements that are in green, those are metals. And the elements that are in blue, those are nonmetals. And then the elements that are pink, those guys are called metalloids. And so they sort of act like metals sometimes and sort of act like nonmetals sometimes, depends on the situation. So carbon and oxygen are both blue. So that's a covalent molecule. And the other way to mix things up is if I take something from the green or pink column and mix it with something from the blue columns. So any of the metals with nonmetals or metalloids with metals, those guys turn out to be ionic compounds. So salts in essence. So if I see something and it's stuff from the periodic table where everything's blue, then I can use this nomenclature where I get to use the dis and the tris and whatnot. So the only caveat, there's 2 caveats with this. If the first one is by itself, you do not say mono. But that's only if the first element is by itself. So what's the name of this molecule? You know it.
Carbon monoxide.
That's carbon monoxide. So the only time you say mono is if the second element in the compound is by itself. If the first one's by itself, you just say its name and don't worry about it. Like nobody says monocarbon dioxide or monocarbon monoxide. They could, and they'd probably be more clear. It's just nobody does. So what about this molecule? What would you call that one?
Nitrogen.
Go ahead.
No, it's not.
Yeah, that's it. So
Or monoxide.
yeah, nitrogen monoxide. So this one is carbon monoxide, and this one is nitrogen monoxide. But what about this one? Sorry.
Nitrogen oxide.
Nope.
Mm.
The 2 is referencing the N.
Nitrogen dioxide.
No, dioxide would be, what you just said would be NO2. That's nitrogen dioxide. So what's this one?
Dinitrogen
Dinitrogen
monoxide.
monoxide. Yeah. So this one is nitrogen monoxide, and this one is dinitrogen monoxide. What would this one be?
Trinitrogen.
Trinitrogen monoxide. And this one?
Tetra.
Tetra what?
I don't know.
Nitrogen.
It hasn't, nothing's changed. It's still
Nitrogen
tetranitrogen.
tetramonoxide. I don't know.
Tetranitrogen monoxide.
Tetranitrogen monoxide. Yep, that's it.
That's a tongue twister.
A little bit. How about
Tetra. So when the number's in front, when you've got the big number in front of all the letters,
yes?
how does that
It-
how does that work? What does that
It doesn't count for naming. So
Okay.
like 2 N2 O5.
Uh-huh.
This 2 is just saying 2 of whatever comes next, right?
Is that like the number of molecules then?
Yep.
Or,
That's a coefficient. It's the number of molecules. So
Okay.
if you had a cat and then you had another cat, just because you have 2 cats doesn't change the name of them being cats, right? So this is tell me what the name of this molecule is. N2O5.
I
What-
forgot what 5 is.
So well, tell me. Let's start it off. What's this? 2 is what?
Di.
Okay, di what?
Nitrogen.
Nitrogen. What's this one? What's the name of the building that we make war plans in?
Pentagon.
Pentagon. So this is what?
Okay. Pentoxide.
Pentoxide. Yep. So
That's the thing.
dinitrogen pentoxide.
Oh yeah.
Okay.
So the way that it works for these covalent molecules is you acknowledge the number of atoms, then the atom, and then the next atom's number, and then the atom. Does that make sense? So the first thing we say is that comes first, that comes next, and then that would come last. So let's try another one. How about I don't know. Doesn't even really matter. Let's see, 8H. I don't know. Let's do 9 just for the heck of it. So what's the first thing that you're going to say?
The 8, which is octacarbon.
Octacarbon.
Octane.
Octacarbon. Okay. Now what? So I say the number, and then I say the name of the atom, and then I do it again. So I say the number. So what's the number?
Nano.
No, not nano.
Nona.
Nona.
Nana.
Nonohydrogen.
And then the one thing we haven't talked about yet is all of these things. I hack the end of the name off and ide. So what's the, do you guys know what the chemical name is for table salt? That's the
Sodium
chemical
chloride.
formula. Sodium chloride. So this is a sodium atom and a chlorine atom, but we don't say sodium chlorine, we say sodium chloride. So we're all of these things, we throw that IDE on the end of it. Okay? So regardless of what it is that you're looking at, you're just going to hack the end of the second substance name off and put the suffix IDE on.
Let's do another one.
Okay. How about S3BR6? So what comes first? What are you always starting with?
3.
So you're always going to tell me, the first thing you're going to do is tell me how many of the first thing that there are, and then tell me what the first thing is, and then tell me how many of the second thing there are, and then tell me what that second thing is. So this is, what do I say?
Sulfur.
So you didn't, did you, it's try?
Try. Can you hear me?
What I hear, like, I miss like your, whatever the first syllable is or whatever it is you say. So I didn't, all I heard was sulfur.
Yeah, trisulfur. I forget what 6 is.
What's 6? What's a
Hexa.
6-sided figure?
Hexa.
Hexa.
Hexagon.
Right, like a hexagon. Hexa,
What is BR?
Bromide.
bromide. Yep. So it's always going to be the number and its prefix and the first substance and then the number of the second thing and then its name with that IDE tacked onto the end.
E on the end.
We good with that?
Why is the IDE on the end?
I don't know why. Why are stop signs red? It's
It's just like every time you're writing this stuff out, it's gonna have an IDE at the end.
yes.
Okay.
It is what they decided to do in 1909 when they did all of this.
Okay.
So I know this is confusing, but this could be way worse because the name of this molecule is trisulfur hexabromide everywhere on the planet. I mean everywhere on the planet. If you're standing in Mandarin, China, you say trisulfur hexabromide, even though those are completely unnatural sounds. There isn't a Chinese word for it. That's the name of it. So you're at least lucky enough that at least the language of chemistry is English.
All of these chemicals mix. Do all of these chemicals attach to each other?
No. No.
Okay.
Are you asking me, like, does this molecule right here exist?
Yeah.
Maybe. I don't know.
Okay.
I'm just making some up so we get the prefixes and the names down. When we were, I don't actually know about this one, but this was painful for me to write because I know that doesn't exist. Sorry. And I know that doesn't exist, so that hurt. But I mean, it was helpful for us to understand how to use the prefixes. So even if it's a molecule that doesn't exist, you can still name the thing. Because maybe it might exist someplace and we've just never done it. That kind of stuff.
Is there a rule for molecules?
There's zillions of rules. Mm-hmm.
Oh, I was hoping for just a couple.
Yeah, no, I'm sorry. It's got a lot to do with what they do with their electrons when they react. So an example would be everybody in the first column likes to, of the periodic table, they all like to give away 1 electron. And everything in the column that's got fluorine in it, they all like to take 1 electron. So if I'm going to mess with stuff from the first column and stuff from the 17th column, the second to last column, does this make sense? That's the formula? If I put a chunk of sodium into a container that's got a bunch of gaseous chlorine, I end up with NaCl's and nothing else. There will be no other molecules made. And the reason is because stuff from the first column likes to give away one electron. And when it does, that makes it positively charged. And chlorines like to gain one electron. And so since electrons are negative, that makes them negatively charged. And then we talked about how opposites attract. So a sodium and a chlorine would just like to bump into each other and hold on. So you will, like, this can't exist. It can't. We can name it, but it doesn't exist. So as far as like how you know what stuff hooks up, we're not going to do that in this class. You were going to take the other class, we would totally do that for like 2 weeks. But we're not going to do that in this class. I just want you to be able to look at it and name them.
Okay. Next class up from this.
Yeah, 121 is the class up from this one. I did have a student in this class in the spring last year and then took 121 in the fall. She did really well. Okay. I think we sort of tore apart chapter 1. Is there something else from chapter 1 we want to talk about?
One about to start on 2 here.
I gotta go turn something off my daughter turned on because it's driving me crazy. I'll be right back.
Okay.
She has one of those mats that's a piano, and she left something on top of it, so it just kept beeping. Did you guys come up with something?
How are we like turning in our stuff? Do we like have to write it all out on Moodle for like our reading? Because
Yeah,
I tried sending the pictures and it like worked, but it was like really difficult.
Yeah, the best thing to do is just type it into like a Word document or a Google Doc or something like that, and then post it in Moodle. Yes.
Alright.
We're supposed to name pictures.
Name pictures.
That's what I didn't get. Like, I'm just supposed to explain like what each table
Oh yeah, yeah.
says.
So like, I don't know why on like why did they put the figure 1.2 in? Like, explain why figure 1.2 is there. Like, give me a sentence on why would they have bothered to include that particular graphic?
What air is made out of?
Yes.
And you want that included in our reading summary?
It's part of the instructions.
Okay.
So just the figures, not the table. I guess we can't really explain the tables.
Well, everything that isn't text.
Everything that's like a picture, table, charts.
Yep, yep.
Okay.
What about this picture of clouds? Figure 1.3. Okay. Never mind.
Okay. Something else? No? Okay. I guess I call it a night and post these things up. If you have any questions, go ahead and post them on the forum and we'll answer. Thanks for
So we'll have audio this time.
yeah, thanks for putting up with all this. Well, at least audio from me, not necessarily audio from you for an extended period of time.
Yeah.
I'm ordering new stuff because this is ridiculous. Okay.